Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Hey, it's my pleasure to introduce Bin Kim, have her here for a talk today. Let's see, you graduated from CSAIL MIT, what, in the last year or so?
Yeah, this year.
Okay, great.
This summer.
So, and you've been at AI2, the Allen Institute for Artificial Intelligence, what, 6 months now?
2 months.
2 months, okay. So you're very new to the Seattle area, so the weather will get better in 6 months. So. Anyway, Bin Kim's she's been doing research in interactive machine learning, and she's going to talk about that today. So, yeah. Welcome.
Thanks for the introduction, and thanks for inviting me to speak at MSR here today. Today I'm going to talk about my PhD work on interactive and interpretable machine learning for human-machine collaboration. The vision of my research is harness the relative strength of humans and machine learning models. Humans have years of accumulated domain expert knowledge that machine learning models may not have, whereas machine learning models is able to perform complex computations efficiently and precisely. The goal of this work is to have them work together in order to help humans to make better decisions. When we want to achieve that, we need machine learning models that could intuitively explain to humans what are the results of machine learning methods for humans that may not be machine learning experts. We also need machine learning models that can incorporate human domain experts' knowledge back to the system in order to leverage that. So my research objectives are developing machine learning models that are inspired by how humans think that could first infer decisions of humans. We first need to know what decisions humans has made in order to maybe make a better suggestion. So I built a model that could infer humans' decisions from human team planning conversation for disaster response. The next part is about building a machine learning model that can make sense to humans, clustering methods that could intuitively explain to humans what the results are trying to say. And finally, to close this feedback loop, I built a machine learning system that could incorporate human domain expert knowledge back to the machine learning system, implemented and verified in a real-world domain, computer science education. And I'll talk about that today. So among these 3 portions, I'm going to focus on these last 2 sections of my thesis, make sense to humans and interact with humans. So let's jump right into building machine learning models that could communicate intuitively to humans about its machine learning results. When you think about building machine learning models that could intuitively explain and communicate with humans, you have to maybe first think about how humans think. There has been rich cognitive research that shows that the way that humans make tactical decisions are based on exemplar-based reasoning. In particularly, if you're a skilled firefighter, the way that you figure out what you were going to do with this new incident, maybe new fire, is you think about all the previous incidents that you have dealt with, think about the closest example to your new case, and apply the modified solution to this new case. So I argued that if we want to build a machine that could support better human decision-making, we need to represent the information in the way that humans think. Yeah?
Can I, my intuition is exactly the opposite. So if I want to teach another human how to buy a car, I could go and point good car, bad car, or I could teach by feature, which is you should look at the reliability record, you should buy a Honda, you should look at those are features. So I teach by feature, I don't teach by example. You teach by feature.
Yeah, so I think so imagine a case where it's not a car anymore. Imagine a data point where you have thousands of features. Can you teach that 1,000 features and enumerate all the features to humans? It might be difficult, right?
But
it's a
in
scalability.
Most cases, I will enumerate just a few features. I said we have to look there.
Right. I think that is a really good point. In fact, the work that I do here is roughly what you are saying, sparsity, pursuing sparsity. So example with features that are important. And those are the ones that I point out along with the example.
Oh, I see. So you teach individual feature by example.
Yes.
So you still teach by feature, but you teach individual feature by example.
Yeah, yeah. So example with the features that really matters, yeah.
Actually, there's an example that supports this. If you want to teach a pigeon how to add, I love this example. The first thing you do is that you put a piece of tape in the cage and you reward for being in the right half. So you're teaching by example, but being in the right half of the cage is a feature. Once you teach that, you move the tape, then you reward for pecking on the wall, then you reward. And in some way, each of these is a feature, but each of these features is taught by example.
Right, that's
So
true.
it's
Very similar idea, exactly. Yeah, but this idea of example-based is really motivated by, people study humans. When they study these people making important critical decisions, the way that humans' brain works is by example. So it's to leverage that sort of rich cognitive research as a start. And leveraging the examples and intuitiveness of examples has been studied. It's not new. In classical AI, it's called the case-based reasoning. Case-based reasoning has been applied to various applications successfully, but case-based reasoning always requires labels. So if you're trying to apply case-based reasoning to fix your car, for example, you need to know all the previous cases that you tried to fix your car. What are the symptoms, and in order to decide what's the solution that's appropriate to fix your car right now. It does not also scale very well to complex problems. I think going back to your question, if fixing your car requires you to read pages and pages of document, it starts to lose that intuitiveness. And of course, it's not designed to leverage global patterns of the data. We do have machine learning models that could leverage global patterns of data, and in particularly related work is interpretable models. There are decision trees or sparse linear classifiers, and in order to do this, and what I mean by sparsity, which I just said, is if you give me high-dimensional data points, then I'm going to select the subset of the features that are important and give it to you so that we can scale to complex problems. My work is about combining these two by maintaining the intuitiveness using examples while leveraging global patterns of the data using machine learning, but pursue sparsity so that we can scale to large complex problems. So our approach, we call it Bayesian Case Model. Formally, we leverage the power of examples, which we call prototypes, and subspaces. These are hot features that are important. And this is just a way to say, we have this complicated thing, that important thing that we would like to explain it to you, and we're going to explain it to you using examples. Formally, we combine Bayesian generative models with case-based reasoning. So let me explain to you how BCM works using examples. So these are set of recipe data where a data point consists of list of ingredients to cook the food. It's not about instruction, but just a list of the ingredients that you need to cook it. And if you look at it, can you cluster these data set into, say, 3 clusters? Crepes, yeah. Meat? Oh,
Is it meat?
Mexican?
Oh,
yeah, Mexican, yes. And there's one more.
Strawberry.
Yes, so strawberry dessert thing. So those are 3 clusters. So one way to cluster this data set is Mexican food, crepe cluster, and dessert cluster. BCM is the clustering method where it clusters this data in an unsupervised manner, at the same time tries to learn what's the best way to explain each cluster. So in this case, someone said it's a Mexican food. We're lucky in this case because we had somehow name for this cluster to describe this cluster, some abstract higher level idea. But if you worked with real data, we often, when we cluster a data, we don't have a convenient name to describe succinctly a cluster. So instead, I can explain to you this cluster as, well, the first cluster is like taco. If you've eaten tacos, you know what's in there. But really, the important ingredients that defines this cluster as a group are salsa, sour cream, and avocado. And the second cluster is like basic crepe recipe, where important ingredients are flour and egg. And last cluster is like chocolate berry tart. Important ingredients are chocolate and strawberry.
So here's my comment to these 2 slides.
Yeah.
You should do a user study where you can see whether people can understand this information faster than your previous slide.
This
Because your
information
previous
faster
slide,
than this slide.
This slide to me, I see the clusters much more clearly. I understand them much faster. I don't have to read anything.
I have a human experiment
in
that I'll
the previous
show you
slide, I couldn't easily see the clusters. Once you put things together like this, I can see the clusters.
So the entire bird eye view of all the data points, that's what you're saying.
This is better than the previous slide.
Previous, this is
You have 3 slides.
No, the one before.
The one before.
So
That's
this is
hard.
not good. This is a jumble.
Yeah.
This is good. I see what the
Right,
clusters
right,
are.
right.
The next one is not as good as the previous one.
Oh,
for me.
interesting. So you would like to see all the data points as
If I
it
see
is.
cluster B, I know what it is, right? I don't have to read anything. I see them and I instantly know what it is. Cluster C the same, cluster A the same. Without looking at the ingredients, without reading anything.
I see.
I'd rather see 5 examples of cluster B than 1 example and explanation.
Oh, I
For
see
me,
what you mean.
anyways.
You want
So
to
I
see
wonder
multiple
what
examples.
most people are like. Are they visual like this, or are they methodical like what you have on the next
I see.
slide?
So this one is a way of, I randomly selected examples, right? And you're saying that, oh, multiple examples are better than just one example and
So these are
subspace.
visual.
Yeah.
If
Yes.
I were to give you like 100
Yes, these are visual.
cases of lawyer lawsuits,
Yeah.
it would be very hard to
Well, but my answer is counting grids. I can see the clouds and so on. But somehow I want to turn it into something I can just spot rather than read through, right?
So I have a human.
But for recipes, it would be interesting to see whether it's really true. I don't know if it's actually true. Is it just me, or some people see it this way, and other people actually really prefer to just see 3 ingredients and read them, rather than to see these things.
That's interesting. Actually, I prefer the ingredients.
The ingredients?
Yeah.
So we have a human subject
Yeah.
experiment. Like I think there are. I talked about this in the later slides where.
I don't think about it. I don't have to think, but I see the graphs. I know exactly what it is.
Where I talk about people prefer different way, and depending on what domain experts that you're working with, people have different preferences.
Yeah.
And the interactive system that later in my talk is going to talk about what are the different ways, not exactly in the way that you said, example versus distribution of the data, but how can we leverage what the preference of the domain expert want bring it back to the machine learning system. But to answer your question briefly, and I'll show you in the later slides, we have a human subject experiment to compare this sort of representation versus not exactly like this, but non-example based methods. So instead this, I show you sort of distribution of hot features of each clusters. So I'll show you that in a bit. All right, so BCM performs joint inference on cluster labels and explanations, which are provided in the form of prototypes and subspaces. Informally, we define prototypes to be quintessential observation that best represents the cluster, subspace to be sets of important features and characterizing the clusters. So there are 2 parts in BCM, clustering and learning explanation. Remember that in the inference step, these 2 happen simultaneously, but for the sake of explaining, I will divide this into 2 parts and explain. So first, clustering part, we leverage widely used model called Admixture model. This is something that LDA uses as well. And what Admixture model does, and also allows flexibility in that way, is that it assigns multiple cluster labels for a data point. So as opposed to assigning one cluster label to one data point. So if you take this sort of new data point, say this is a Mexican-inspired crepe, and I talked about this in front of my friend from France, and he got a little offended, like, what are you talking about, Mexican-inspired crepe? But if you have such recipe, then what Admixture model would do is assign the ingredients that belong to Mexican cluster to be cluster A, and other ingredients that belong to crepe cluster to be cluster B. So you can think about you are building a vector of Z where it's got some A's and some B's. You can think about another example where we have a crepe that has chocolate and strawberry. So some of the ingredients, chocolate and strawberry, will belong to cluster C, where the other ingredients like crepe belongs to cluster B. And you can also think about normalizing this vector to get cluster distribution vector. And that's a pi vector. It's a common representation of Admixture model, pi vector right here. And if you combine that with the supervised learning method, you can use it to evaluate your performance, clustering performance. And that's exactly how it's done in LDA paper. And that's exactly how we evaluate our model. Thanks to nice conjugate prior you have some control over how you want the cluster labels to be distributed using the hyperparameter alpha. The next part is learning explanation part. we have prototypes and subspaces as a way to explain clustering results. And the first prototype is in the generative story. Remember, it's not the going up to the inference story, but in the generative story, prototype is simply a uniform distribution over the data point that you gave me. And this is the key portion why iBCM is intuitive, because if you're a doctor and you gave me patient data, patients that you have dealt with last decade maybe, then I will cluster them. And the way that I will explain each cluster is using one of the patients that you dealt with. Subspaces are simply binary variable, 1 for important features and 0 for not important features. And together with prototype, subspaces forms this function G that feeds into sample the phi latent variable, which describes characteristics of clusters. So what is this function G? Well, function G is really simply a similarity measure. And you can use any similarity measure that you want, but this is the similarity measure that we used. This looks complicated, but this is actually the simplest possible similarity measure that you can think of. It says, if you have a feature that is in the subspace, and you have the same feature value as your prototype, then I'm going to score higher than other data point that doesn't have that feature. So if I'm a taco, and prototype is a taco, and I'm a taco salad, I share avocado and sour cream with my prototype, so I will score higher than, say, chocolate berry tart.
So in your, go back to the N part, right? Does that mean you have a closed universe assumption that we cannot accept new items in this model?
So I will not create a new item.
You will not generate a new item in this model.
And if I do, the assumption here is that would lose intuitive. You give me patient data, and I'll generate some fictional patient that you never dealt with. So
what is being generated in this model? I'm a bit confused now.
So you're familiar with like LDA generative model story, right? So this is just generative story how I.
But you're not sampling new documents or anything, right? You're not sampling new patients.
I am not sampling new patients, right?
Or are you saying you could generate new patients, but just take another set as the set for the purpose of getting prototypes? Like, do you have that N, right? And that N is limiting how many items you can have in a system?
I see.
Or is that not true? You can actually produce, in your model, can produce item N plus 1.
So the answer to that is yes or no. So yes, I can. It's a generative model, so you can generate fictional prototype. But one of the point of this model is doing so would decrease how intuitive this model could be.
Because in the end, you use the generative model for interpreting the parameters, right? You're going to look at all the parameters and tell a story about it instead of fitting new items. That's the purpose of the model.
Right.
Am I correct?
Right.
Comment on that. So generating examples is really dangerous in a complex domain because you'll get some detail probably wrong. I mean, in healthcare, for example, if you were to generate a patient and you got something wrong, like you suddenly had a male who was pregnant, unless you had sort of perfect generative structure, you might make those kinds of mistakes. Yeah. And then experts just immediately will ignore everything you do because it's sort of nonsensical.
In some ways,
so using real examples is sort of safe because they must exist.
It's the same for LDA story. Although it's generative, nobody in their right mind would actually generate new documents with LDA, right? It's a matter of looking at the topics, and I imagine the story is similar.
Yeah, exactly, yeah. Really good example. All right. So in G function is similarity measure, and you can use other similarity measures such as loss functions. It's a pretty general model. You can pick similarity measure that fits your application. So when I'm working with interpretable models, I can't just show you that here, this is a model, I cluster data well, take it. That's not how it works. We have to answer all these questions in order to convince you that I built something interpretable. So first is sanity check. You said that you learn prototypes and subspaces. Does it learn intuitive, make prototypes and subspaces that make sense? And second, if it's true, well, interpretability is great, but we don't really want to sacrifice performance for interpretability. Does it maintain? And also lastly, if all the two are true, then can this really improve human understanding about the clustering results? So I'll present BCM's results by answering each of these questions. We ran BCM on two publicly available data sets. First one is a recipe data set. This is from Computer Cooking Contest. One data point is, again, like a list of ingredients here. First one, it says soy sauce, chicken, sugar, sesame seeds, and rice. So it's a list of ingredients as features, Boolean features. It's making something Asian-inspired chicken dish. So those are a data point. When I ran BCM on this recipe data, we learned 4 clusters. The first one looks a lot like pasta cluster, and it selects Irvin tomato in pasta as its prototype. And it learns oil, pasta, pepper, and tomato as an important set of features. And the second cluster, which looks a lot like a chili cluster, selects generic chili recipe as its prototype and learns beer, chili powder, tomato as its subspace. And if you're like one of my committee member who, when I showed this to her and she was like, Bean, something's weird, beer should not be in chili, something you gotta double check your model. And if you are wondering about the same thing, I highly recommend that you should start putting beer in your chili, because it really makes a lot of things better, right? You can pour it in your stir fry. Beer makes a lot of things better, like triple, quadruple in particular. And we also have a brownie cluster. Select microwave brownie as its prototype, selecting baking powder and chocolate as its subspace.
So the words you're showing are the words from that particular recipe.
That's correct.
And then you just highlight the ones that are the most likely, or
important ingredients that describes the cluster.
Is there any hierarchy to the clustering, or is it a one level?
It's one level right now, but I think we can extend it to hierarchical. Yes?
So can you say something about your inference algorithm?
How do I perform
Yes.
inference? Yeah, it's coming, but I perform collapse skip sampling.
You do have discrete variables here, right?
I do.
Okay. Is it easy to do sampling? Like, does it behave nicely?
There's like some art about making Gibbs sampling work, right? It's about all of hyperparameter.
You found it to be
Everything.
okay.
I find it to be okay, and I kind of learned, this is not my first Bayesian generative model, I learned how to make it behave itself. But I think there are a lot of other inference techniques like variation inference that could also be applied to this model if I sit down and work out the conjugacy. Okay, and another data.
What about that naive approach where you just run your LDA or whatever on this data, and then for every one of the clusters, you find the typical recipe and just show that?
Yes, that would be another example. In fact, my human subject experiment explored that exact way in a slightly different. It doesn't pick example, but it shows like a list of ingredients that really looks a lot like a recipe. All right, another data set that I ran BCM on is handwritten digit data. This is USPS handwritten digit data. And I'm showing you 5 different clusters on the right. I zoomed in one of the cluster on the left. The first row is showing how it learns prototype as the Gibbs sampling iteration goes on from left to right. And the down lower is showing subspace. So you want to see something that doesn't make sense on the left, and hopefully it will make more sense as you move to the right. The prototype, it looks like it's learning digit number 7. And the subspace looks like 7, which makes sense. So these 2 experiments, we're encouraged by these 2 experiments and say, okay, what about the performance? Yes?
Yeah, I thought prototype has to be one of those AND examples.
Yes.
But why do you have those, like, it's not one of the items, actually?
This one?
Yeah.
Yeah, I get this question all the time. It is actually. So I double checked. It's a number 1 in their example. It's really weird. It's a digitally written hand digit data set. So if somebody put the pressure really low, then it's like 1. Yeah, it exists. Okay. What about performance? We compare this clustering performance with LDA because it uses the same admixture model to model underlying data distribution. When we tested it for 2 different data sets, hand digit data set and 20 new scripts, and the green one on the top is BCM, the yellow one is LDA, we show that BCM is able to maintain performance, and often it performs better than LDA. We also perform sensitivity analysis. There are a couple of hyperparameters that we can tweak. We just want to make sure that we're just didn't get lucky by hitting a right hyperparameter. So we tested within a range of values for different hyperparameters and show that the performance doesn't change significantly.
So just to clarify, this is classification, right?
Yep.
So you are representing an object by its topics mixture of weight as the additional, that's the new feature representation.
That's
Is
right,
that
yeah,
what it is?
exactly.
Okay, so here you're saying somehow this transformation maintains class separability.
Yeah, so this is, I spoke briefly earlier, but I kind of went quickly. In LDA paper, the way that they have tried to convince the readers that the clustering performance is good is that they use this cluster distribution as a new feature, just like you said, and combined with SVM to produce this sort of graph and accuracy. And that's exactly what we did.
Not very convincing anyway, but I understand what you're doing, and it's good to see that it's
Yeah, I think it's difficult to put your hand down on the clustering method, right? There are other methods like coherence, topic coherence, or other measurements the topic model and community came up with, and none of these are, it's subjective, it's difficult, you don't have a ground truth. Yeah, it's a difficult problem.
So back to that slide. So can you explain intuitively why this model, the new model BCM, is better than LDA?
It's coming.
It's coming.
Yeah, it's coming. I have a pictorial example of that.
So in this case, you have one prototype per class or
Yes.
per topic. Since you're outperforming in this way because you're having a model that's actually now closer to the data a little bit, because you're using exemplars, why not have more than one per class?
Yeah, I think it would be a good idea to extend the model to have multiple models. It just makes things more expensive when it comes to inference. But I totally agree. There are Tifshirani's work in Stanford where they learn multiple prototypes to cover different ranges of examples. I think that's a great idea, but it's something that I haven't done. Yeah.
So I didn't understand, what are the features to the SVM?
So features to the SVM are this pi vector that describes cluster distribution. So I show you the Z vector where it collects A's and B's and C's. You normalize them to get distribution vector. So like parameter for multinomial distribution. So it's just like LDA. Okay. So pictorial example to answer your question. Pictorial example of why this might be true, right? If you think about posterior distribution of LDA and think about a level set where all the solutions on that level set scores equally in LDA model. LDA would pick any of these because they're equally good. But what BCM is trying to do is pushing this solution towards some other point that is also equally good in terms of clustering, but also interpretable for humans. Because in posterior of BCM, this point would score higher than this point. Or you can also think about how the way that BCM characterizes the cluster is working as a really smart regularizer for this model.
So do you think human interpretability effectively creates a sort of margin?
Yeah, that's how I intuitively understand why this might be the case. Or another example that you briefly mentioned, because we are clustering around examples, maybe that gives a rise to a better solution, because it exists.
You are using the same number of topics
As LDA.
as LDA.
Yeah.
I have a simpler explanation for what's happening there. Your model, an LDA model, cannot capture all the correlations in the data.
Yes.
But the data has those correlations, and you're using the data in your model. So that's why you're getting a sort of hybrid thing that captures these higher level correlations that are not there, complex correlations that are not there.
Yes, exactly. That as well. Mm-hmm.
That's why I'm saying maybe multiple examples is even better.
Mm.
And then, of course, in the limit, you have to compare with the neighbors' approaches.
Right, exactly.
Right? Because
yeah, and automatically learn how many examples do I need to learn the example. Yeah, that would be definitely a good way to expand this work. All right, and we already talked about this, but I perform collapsive Gibbs sampling to do this. This is equations that I didn't mean to walk you through it, but you can see that we see some better functions by integrating functions. We integrate out phi's and pi's because we don't need them, but we can forward generate those cluster distributions if we want to. So the last experiment that I did is, does this learned representation or explanation make sense to humans? One way to measure this is taking subjective measures. So you have people come in and you ask them whether you like explanation A versus B. Better way to do this, in my opinion, is taking objective measure of human understanding by asking humans to be a human classifier. So we explain 4 to 5 clusters using the 2 different methods, BCM and LDA. Then we give them a new data point, then ask them to classify where is this new data point belong to. And we measure how accurately they can do that. When cluster is explained by BCM, it looks like list of ingredients. We don't give them the name of the dish because that would be too easy. And when it's explained by BCM, it makes a dish. It's a dish. It's an example. When explained by LDA, it's the top K topic or ingredients for each of the clusters. So it looks a lot like that it will make a dish, but it does not make a dish. So it's not an example.
Can you say that again? I didn't quite get it.
How the clusters are...
How they are presented.
So this is a example. This example that I pointed out earlier, this is about some Asian chicken dish. This is a dish. This is the ingredients that makes that dish. This is an example.
So this is a particular example in your big N
That's
corpus,
right.
right?
Yeah,
So
yeah.
that's one of them.
Whereas LDA, I will just select top K ingredients of each cluster, where when you look at it, it looks a lot like a dish,
I see.
but it does not make a dish.
It seems that there's two things going on there. There's the prototype, and there's the fact that you have a real example, right? So I could take LDA and then randomly sample a data point, and then look at its argmax cluster and see if the person agreed with it.
Randomly sample among the examples that belong to a particular cluster.
Yeah, or just randomly sample a data. I mean, so the point is that the prototype is special because it somehow maximally represents the cluster versus an arbitrary guy in the cluster. And so both things are being, both differences are here.
For the highest likelihood guy in the cluster.
Yeah.
Or like perhaps salt isn't everything, so it's not a good predictor, but if you don't have salt present in a recipe, then it doesn't meet people's perception of a recipe. Because
Right,
every
right.
recipe has salt.
Yeah, true. There wasn't a question, right? It was a comment.
Well, okay, so but so I'm suggesting that maybe the comparison is a little unfair in the sense that you're giving BCM not only a prototype but a real example that LDA doesn't get. But I could have LDA prime that returns a real example as opposed to top features.
Right. So we could compare the same sort of like a nearest neighbor example where
What I mentioned earlier, after LDA you just pick the prototypes.
Right.
So
As
part of the
opposed to
learning.
processing. Yeah, we could do that. I think that the way that I didn't want to add on to, that could be a perfectly good baseline that we didn't test.
Can you say something about your test dishes?
Yeah.
Where do you choose them from?
Where is it coming from?
Yeah.
It's one of the data point from the data set that I mentioned earlier.
So it's part of it's one of those N things.
It's one of those end things, yeah. Because it's a new example. As a classifier, you take a new data and you classify them.
What do you mean a new example? So my question is, do you leave that one out when you train your model?
Oh, I see. Yeah, of course, yeah.
So you actually have to try a whole bunch of models, leaving a bunch of dishes out, or?
Why would I need that?
I'm just asking you.
Oh.
Your specific dish, that test dish,
Would it be left
came
out
from your original purpose, right?
Yeah.
But when you train your model, when you train your iBCM model, was that in the training set?
No, it shouldn't be, right? Because then it will be.
So what's your protocol? Did you leave a bunch of dishes out up front?
Oh, I see. Up front. Oh, I see. Yes, of course, yeah.
So that's what you did.
Yeah.
How much did you leave out?
I asked 16 questions for people, so I think I left out about 20 dishes out when I was doing clustering.
And the true label of a dish, how is that determined?
So it's determined, these are all really good questions. So it's determined based on its name. So we know we had 2 independent human annotators, and it's often done in human subject experiment, and we have them sort of give them a classes that they can label each dishes to, and they label them. And if you look at it as a human, it's pretty obvious which cluster that this would belong to.
Wait, the clusters,
And that's how I get to
sorry to dwell on this, but the clusters are with respect to what the BCM model discovered, right? So have you compared against the pure computer system where you train on all n items and just see where those guys fall, where those dishes fall into, by your BCM model.
So assuming that they will come up with some other clusters than what has been tested?
Right, okay, I see the problem.
Okay.
We can talk about this offline.
Great.
So when people do this, they are labeling a new recipe. They're doing admixture of the new recipe with respect to names, and they're using name dish 1, dish 2.
Yeah. So we don't give them actual name of the dish.
And so they have to name it as dish 1 and dish 2. And do they? How much time do they spend analyzing this? Because there's a complexity here. Because now I, as a human subject, have to read the recipe, understand it. I do a lot of now processing. So if I spend very little time, I might be confused. I might be learning on the task, and the early examples I do wrong, later ones I do better.
Yeah.
Then also, if I'm allowed to name these things, I might do better.
Interesting.
If I'm allowed to name them. If I'm asked to draw what the recipe is going to look like at the end or make the recipe, I may do even better. So I don't know how that's.
I see.
It's a confounding factor, but also it's kind of an interesting research question.
Right.
So I don't know. What are your experiences regarding that? I know that was not a target, but
it's a part of the experiment where you make sure that in terms of the ordering, the later one you do better than the first one. We randomly, or we have the perfect latent squared, just so that which question was presented earlier for one participant will present it later some other participants, so that we can have a balance in impact. And in terms of naming thing, we actually had first pilot study. We struggled to set people to the same granularity of recipes. What I mean by that is when I show them the cluster, they were thinking, is it this holiday brownie or is this mint brownie? That's kind of granularity they were thinking. So we were like, okay, no, it's not. So we gave them categories of candidate, including some of the ones that represented it here as a cluster and some of the other things of the same level of hierarchy, so that to prime them to think about in this sort of level of a space.
They get these dishes, but then they get a few examples, practice examples where they can understand what
there's
what's being asked.
Yeah. Okay. And so when we did that, you probably already read this by now, we have 24 people, 384 classification questions. We got statistically significant results. And what this is showing you is that, okay, this model learns reasonable prototypes and subspaces, maintains performance, and it can improve human understanding for the test that we tested. So moving on to the next part. Closing, at the beginning of the talk, I talked about how we want to leverage human domain expert knowledge back to the machine learning systems. And in this part of work, I extended BCM in order to incorporate human domain expert knowledge and implemented this for real-world application, the computer science education domain. So before going into detail, and I feel like this crowd would buy into this idea, let me convince you why interactiveness is important. So this is the data set that I've shown you in the beginning of the talk. And I showed you that one way to cluster this data, and we worked this out together, is Mexican food, crepe, and chocolate berry tart. But if you're an owner of a restaurant and you're trying to hire a pastry chef, the way that might be really useful for you to cluster your menu items might be this: savory food on the left, sweet food on the right. So that when you're evaluating your candidate, you want to make sure that they can cook these things. What this is trying to tell you is that depending on what you are trying to do with this clustering results, what is most useful could be different. And I'm arguing that trying to figure that out interactively is a good idea. And of course, leveraging interactiveness to deliver better clustering or classification results has been studied. A lot of people in MSR had studied this idea. Some of them assume that the users know machine learning, so we help them to better explore hyperparameters or modal parameter settings, assuming that they know what different hyperparameter settings would influence the performance. Or some other work had assumed some simplified medium for communication. So users would internalize this medium to be something, communicate through this medium, and machine learning would take this medium, transform into something that makes sense to machines. But it could be potentially, these two could be potentially different. The work that I'm suggesting here provides a unified framework where humans and machines can talk and communicate using the same exact medium, prototypes and subspaces. So we made BCM to be interactive. We called it iBCM by making prototypes and subspaces and another node to be what we call interactive latent variables. These are like latent variables, but not quite, because not only these nodes are inferred, values of these nodes are inferred from the data, but also feedback from humans. The key part why making interactive system is difficult is because you want to balance what data is trying to say and what humans are trying to say. You don't want to completely override what data is trying to say with what humans said, but at the same time, you don't want to completely neglect what human is trying to say. And so our approach is decomposing Gibbs sampling steps to adjust the feedback propagation depending on their confidence. And also, since we're working with an interactive system, we want to make sure that the response time is really quick. You can't have them wait forever. So we accelerate the inference by rearranging the latent variables. In the high level, without going too much into detail, we first listen to users, then we propagate users' feedback to accelerate inference, then reflect the patterns of the data. We tested this to 2 different domains. First one is abstract domain, and then I'm going to show you the real-world domain. Abstract domain is useful because we have a control over how we are going to make the distributions of the data to be. And in this case, we have generated this data such that there are multiple optimal ways to cluster the data. This is the interface that humans used to interact with our system. Each row is a cluster, so I'm showing you 4 clusters. The first column is a prototype, so the second row, it says the data point 74 is the prototype of this cluster. And on the right, I show you the features that it has along with subspaces. So if it has check marks, it's got round patterns, and it's triangle, and it's yellow. But only these 2 features are in the subspaces. So it's a triangle and yellow. And if you look at on the right, which shows other items in that group, it all has triangles, and it's colored yellow. There are 2 things users can do. You can click one of the check mark to change to star check mark to include that feature into subspace. You could click the star check mark to make it into check mark to exclude that feature from the subspace. Then you can also click any of these items to promote that item to replace the prototype of any of these clusters.
So the first cluster was the data overrode the round pattern star.
Say it again.
Your first row, there you have a starred feature called round pattern.
Yeah.
That I assume is the not lines.
Oh,
So
yeah.
the
But
data has overridden the user's feedback and said, well, I'm going to throw lines in there because that's what the data says.
yeah, so that maintaining that balance is difficult. That's the part of what this is trying to do. The way that we ran this experiment is we first show the subjects randomly arrange this whole data set. And then we ask them, what is it the way that you prefer to cluster this data set? So in order to sort of learn the inherent or underlying their preference. Then we show the results from BCM. So what essentially this does is it selects one of the optimal way to cluster this data. And then we ask subjects, how is this matching with your preferred way to cluster? And we collect that data according to Likert scale. Then we have subjects interact with iBCM, so they can select, unselect the subspaces, promote the prototype to make this cluster more like what they wanted. And then we ask the same question again to indicate how well the results matches with what they want. We compare the answers collected in these 2 steps. We ask for 24 participants, 192 questions. And subjects had expressed that they agree to a lot more strongly that final clusters match with their preference after the interaction, and that was statistically significant. So encouraged by this idea, we now take this iBCM to a real-world domain, to education. In particular,
test for the placebo effect here? I mean, maybe they just like the final clusters because they contributed.
I see. We collected
a random cluster. I mean, just noise your cluster and show it at the end and say this is a response to what you've said. They might still prefer the new ones to the old ones.
Because they just have a feel like that they've interacted with it?
Yeah, they're committed to it, invested in it.
Interesting idea. So this might be slightly tangent. Well, to answer your question, we didn't test that, the placebo effect. But one of the idea of interactive model is that often when users when they start to interact with the interactive system, they don't actually know what they want. As you interact with it, you kind of learn, okay, oh yeah, right, this is what I wanted. And it's like a way for them to interact with the system to figure out what they want as well. And if the final clustering is really not what they wanted and it's just a simply placebo effect, they would, I personally don't think that would be the case, but it's something that we could totally test.
Can you go back to the previous slide? I think I have a related question here. What do you mean by the first step?
So the first step is actually, so it's something that I could, if I had, the first step is really trying to fetch what humans wanted initially. What are their underlying distributions?
If I'm the subject, am I supposed to arrange those objects into clusters?
I see. No, we asked them what are the features you want each cluster to have, because there are only 6 features here. We said cluster 1, you wanted cluster to have line feature, pattern, color.
I see. But what about what I just suggested? Maybe have the humans just free play and form clusters. Then you have an objective way to measure.
Yeah. The way that I measure this p-value is just simply comparing these two. But you're right. If I had compared it with like original, then the placebo effect could be tested. But I looked at it, scanned it, and I don't have a number for it. But they're roughly similar. But I don't have a number for you right now. I can.
And the features were predefined. You gave them the features.
The features of the abstract data?
Yeah, the circle, red, and so
on. Yeah. Because those are generated.
Have you thought about just letting them come up with features? You just give them an empty table and say you fill in whatever you want.
Oh,
and
interesting.
then other people are using the features that somebody else has come up with and so on.
That's interesting. That would be interesting, but I don't know how we would evaluate that, right? If you're using different features, I guess if only thing I'm gonna take is Likert scale, then I can probably evaluate it. But that would kind of introduce another factor where that defeats the purpose of using abstract domain, because the point of using abstract domain was that we have this clearly defined world where only we allow this many features.
Those 24 participants are the same as the ones from the previous experiment?
No, completely different set. There's no one overlap between those two, because the first people knew that what I was doing, so they couldn't. Okay. So I took the iBCM now, encouraged by the previous results, to the real domain. And the education is particularly appropriate domain for iBCM and interactive machine learning, because teachers has accumulated years of knowledge, or maybe their philosophy of how introductory Python programming class should be taught. And we want to leverage that and deliver something that is useful for them. Currently, in particularly the domain that we were looking at was how they create grading rubric. So exploring student submission, spectrum of student submission for homework problems. Currently, what teachers do is they select randomly 4 to 5 assignments, and they look at them, scan them in order to create the table to grade the homework. But we know that if teachers can understand better the variation of this data, they could provide better tailored feedback for the students, ultimately, hopefully, improve the educational experience for the students. But it's difficult working with coding data because we don't have the obvious features as we do for other types of domains. So we leverage a system that Elena Glassman and Rob Miller at MIT has developed called Overcode, which performs static and dynamic analysis in the code to extract the right features. So we use those. This is the system we built. We have, on the left, we have prototypes. I'm showing you 3 clusters. The last one is blue because it's clicked. When it's clicked, on the right, it's showing you other items, other homework submissions that belong to that cluster. And these are from couple of years of homework submissions that's collected from MIT introductory Python class. And the red rectangles are subspaces, of course, the keywords. And humans can interact with the system using two things. Similarly, unselect, select subspaces, so make a keyword going inside of the red rectangle or not, and also promote certain examples to be prototyped. So if teacher like this prototype, then they could promote this to replace any of the prototype. This experiment, how we perform this experiment is comparing two interactive systems. We made the benchmark system interactive to keep the engagement level fair for both of the interactive systems. The first one is the BCM system, the one I just told you, and the second one is still interactive, where subspaces and prototypes are pre-selected for the users. And the way that this is generated is that we ran BCM with new random initial points, so it converts to different clusters. But it's still optimal according to the internal metric of the clustering method. So when users click that button up there, it just shuffles around and shows you a new cluster. And we invited 12 teachers who previously taught Python, introductory Python class at MIT, and we told them that your job is to explore a full spectrum of student submissions and write down a discovery list. So any features, that interesting things you find when you're looking through this large student submission, write them down. And this is a video of demonstration how the teacher might use the iBCM system. So first, the teacher go to the first cluster, and because while is in the subspace, most of the submissions on the right has while keyword in it. But the teacher scrolls down, okay, everyone used while, until they find something interesting. Some person imported an operator. If you're familiar with Python, this is like importing a library. And teacher's, okay, well, let's take a further look at this by promoting this guy to a prototype, and then indicate what's interesting to the teacher. Then look at all the other people who imported a module. Somebody imported a math, NumPy, iter tools. And then the teacher moves on to the next cluster, checking through this until find something interesting. The student is checking length of these two vectors. And depending on what teacher you're talking to, some people think that's a good idea, some people don't think it's a good idea. So the teacher goes through, update that to the prototype, and continue to investigate the student submissions.
So, did I understand it correctly that you have a fixed number of clusters, hence prototypes?
Yes.
And if I found something potentially interesting, I need to replace one of my existing clusters.
Yes. This is a good question, because that's why the task of how we envisioned this tool could be used was more exploration. It's not about clustering the data set. Once you explored and discovered things from the existing clusters, our idea was that you can forget about that cluster, update with that to some other cluster, make it into a different cluster, and continue to explore.
Yeah, I understand this is essentially what we call island finding new things. But I'm a little bit worried that because of your the iBCM system, would there be like some coupling by the fact I need to push down some existing clusters that might hide some features?
Yeah, totally. Like I feel like we worked on this together or something. Yeah, we had that effect. We saw this. And the way that we had overcome that issue, and I think it's a still really important issue to overcome when you are working on clustering method, interactive clustering method, is that you need to explain how the system works. And explaining that to someone who doesn't know machine learning is still a very challenging problem. That they need to know that these two clusters interact. They share some information. So if you make entire cluster to suck up all the zip, the summations of one particular type, you're not going to get anything like that for the other clusters.
Another potential solution is to go to Bayesian nonparametrics. Instead of a fixed number of topics, you can go the route of things like tertiary processes.
Right, but that doesn't solve the problem of interacting clusters. That only shows you that it's going to be another cluster, that if there exists enough evidence, I'm going to create another cluster.
I can create a new cluster. I can construct a new one.
Right, totally, yeah. But the explain the nature of the clustering method is very difficult. So the way that we did it is we had trained these people to use, this is the behavior that you expect, and now let's use it. Yeah, good points. Okay, so we invited 12 subjects who previously taught the class. We showed them 48 problems, and we asked them 15 Likert scale questions, post-questionnaire, where 12 of them resulted in statistical significance. They fall into one of these categories over here. With iBCM, they said they were more satisfied. They better explored the full spectrum of student submissions. They better identified important features to expand the discovery list. They thought that important features and prototypes are useful. So some other quotes from the participants, they said that iBCM enabled them to go in depth on how students could do. They find it useful in particularly large data set where brute force would not be practical. And this is particularly encouraging because in the rising of MOOC, where teachers now have to teach not just hundreds, but thousands or maybe more students, maybe this interactive system can help them to better explore students' submissions and ultimately deliver better education experience for the students.
But here you can have that same effect I was talking about before, because if you just give them some clusters and they start using them, as opposed to you give them an opportunity to play with the data, understand where clusters are going, come up with almost the same solution themselves, they might prefer that second path to the first path, which doesn't mean the clustering itself is better. Mm-hmm. It means that exposing to technology and making them understand the technology is what actually helps.
I see. That's the experiment that I did in this interactive experiment. That's exactly what I did, right? This is a pre-clustered thing, and this is something that they can interact. Which one they prefer, and they prefer the first one.
Yeah, but then the question is it? Do they prefer this because this whole system helped them learn? Or do they prefer it because they end up with better clusters? I mean, both are valid outcomes.
What do you mean by better clusters here?
So in the end, when they create these new prototypes by moving things around, they get a different set of prototypes than you would have gotten with BCM applied directly.
True,
right?
But BCM
or LDA, then choosing the best matching prototype.
Right. But BCM is also optimal, right? All of these clusters are good. It's just a matter of which one matches with your idea of clusters better.
But even that, the issue is that when you just provide the clusters, I have no idea what the clusters are. When I do this, I get an idea what the clusters are. That doesn't matter. That doesn't mean that.
I see. Just learning about the
clusters. I mean, we could have started with the clusters that you end up with, and you give it to, you run this experiment. You end up with these good prototypes for one teacher. You give these prototypes to the next teacher, and they go back to something else. And if you run this in a circle like this, they might be just going all over the place. They're all happier with the resulting clusters, not because these clusters are better for them, although that's the illusion you get, but simply because by going through all of this, to this exercise, they start understanding the technology.
I see, got it. So this experiment, this second tool kind of gives you that feel by giving you different ways to cluster the data, right? The users can see 5 different, 10 different ways to cluster the same data. That gives you the opportunity to learn.
That's where the value is, rather than in getting the optimal clusters. Maybe they're not getting the optimal clusters. They're just getting a set of clusters, but now they understand what they mean.
So related to this, when is your quantitative measure for this result?
It's the 15 Likert scale type of question, post-questionnaire questions.
But this is done per subject. Like I'm going to evaluate my own.
Yes.
But so maybe one solution is to do a cross-subject evaluation, right? I evaluate your resulting cluster and see if I like that. Then start with something like that.
So we thought about this idea, but then there is another conflict that what we're trying to do here is to leverage that teacher's philosophy of teaching. We have like 10, 12 teachers coming in to the room, and they have really completely different idea of what good homework assignment should. Like the assert example, some people think, oh yeah, of course you gotta check the length of these 2 vectors, like it might break. But there's some teachers like, no, you don't do that, it's a waste of line, you just assume that given inputs are already checked. So these things are very different, and if I ask you to check my results, chances are that, it's probably not ideal for you.
That detects who doesn't like whom, right?
Making a graph of
I'm just saying, like a teacher comes into your system and starts messing things around, sort of like the cat comes onto the mat and she's going to start moving the mat around. The mat is going to be exactly the same when she lies into the mat, but she thinks, well, now it's better than it was before because I've done something to it.
My assumption
And what you do to it is not to it. You're doing something to yourself. You're preparing yourself to lie in the mat.
Right. So my assumption to my work is that like humans are better than that, right? Humans have domain expert knowledge that we can really leverage in this system. That's an assumption to my work.
But it's testable. And either way, it's useful. I mean, I'm not saying even if that's what happens, that the teacher gets used to this tool, that's still useful.
Right. How is it testable that you're doing?
I think that's the answer actually.
Yeah,
Just
I mean, you could test for kind of like coverage or recall of different features, right? So just using the tool collectively, how many different features can be discovered?
So that's one of the so these things we thought about by collecting the discovery list, what they wrote and how much of the coverage that is compared to like the Oracle set of features of the whole student submission. That's all subjective. We have to somehow come up with this Oracle list, which is subjective to begin with, and being able to count when teacher write this feature, the teacher might mean two different things, and that having that just really lined up one by one in Boolean vector, that's really hard. So even calculating this, absolute value measuring this is actually really hard to test. Okay, so I talked about machine learning models that can make sense to humans by building Bayesian case model that could provide intuitive explanations using examples. Then I extended this idea to be interactive, implemented in a real-world domain computer science introductory Python class to show that how this could be useful. I think there are a lot of really exciting things that could be done in interpretable and interactive machine learning models. And one of the things that I worked with briefly, and it deserves a lot more attention, is visualization. When I worked with this idea briefly when I was an intern at Google, where I worked with software engineers whose job is to look at this very complex data on a daily basis and explore the spectrum, which are pattern data. I looked at different feature reduction methods and compared them to see what are the ways to represent the same data such that they could better explore the distributions of the data. Another thing that I think very important, and I think it goes back to our discussion earlier, is that looking at what is really your need in a specific domain. So one of the system or the project that I worked with was working with a medical domain expert who looks at autism spectrum disorder data. For them, meaningful cluster is not just clustering the data, but really figuring out what are the features that distinguishes two different clusters. What's the difference between A and B? What's the difference between B and C? For them to help hypothesis generation, for example. So we built the model to learn those distinguishable features. And another thing that I think a lot of people like Salima at MSR looked at is using this interactiveness as a way to help data scientists to debug models and better explore hyperparameters. And now a lot of companies are hiring data scientists where their daily job is to look at this model, stare at this model, look at what are the hyperparameters that are better fit for my performance, how do I achieve that performance that I want. And I think we can use the interactiveness to really make their job easier and more efficient. So I work at AI2. At AI2, we think one of the problems that will help us to take a step forward in AI is building a machine that can answer fourth grade science exam. And here's an example of fourth grade science exam. It goes, in which environment would a white rabbit be best protected from predators? And the examples are shady forest, snowy field, grassy lawn, and muddy riverbank. When you look at this question as an adult, hopefully you see that, oh, this is about the teacher is trying to test the idea of camouflage. If you know that it's this abstract concept called the camouflage, you might be able to apply that to answer this question. So what I'm trying to do at AI2 is how do we learn these abstract concepts in an unsupervised manner from a large corpus? Once we detect this abstract concept, then maybe we can answer these questions using this sort of abstract idea that humans had defined. And one of the key insights that I think it will help us is that the learned graph that represents this abstract concept should be make sense to humans in order for it to be a concept that humans had decided to define, such as camouflage. And this involves, one of the first ideas that we are exploring is using word-to-vec word embedding representation. This is just learning, mapping a word to a vector in a point in a vector space, and use that sort of representation to learn the context of which it represents the camouflage. And that extends the assumption that I had in my earlier work, where given features to me, the data set has already interpretable features. It's not no longer recipe or patient data. It's some feature that we don't know what they're about.
Can you explain that matrix a little bit better? I'm not quite clear what it is. That matrix on the screen.
Oh, this matrix. It's actually word-to-vec representation of this particular question. I just put it there because I.
So how the entire question is one point?
Just one question.
So this entire question, and then there are answers. So you just it's just a question, not without the answers that's being embedded.
I see. So what I did here to make this matrix is I select a bag of words from the question. This is very preliminary. We're just starting to investigate. And then I expanded them with their neighbors in word-to-vec space to kind of have a smoothing effect. So not only looking at rabbit, I'm going to look at fox, raccoon. And then we cluster them with respect to rows and columns to learn these are the words that commonly co-occur, set of words, and these are the contexts that commonly co-occur. And then I'm hoping to learn a graph out of it. Yeah.
So is there sorting on the?
Yes, they're sorting. Yeah. Well,
they're sorted by.
They're clustered, and these are one cluster in the row. There's another cluster in the row. Yeah. I like how attention is directly going to the matrix, and they just put it there to kind of. And what I think that it will be really interesting topic to work on is that this deep learning has achieved much success in various fields. And I think, in my opinion, one of the drawbacks of deep learning is that it's not interpretable. What we really want to do is for people to gain more insight into this powerful tool and it's ultimately really make better decisions. And this part, looking at how we can assign a learn interpretability from such not interpretable data is another way to interesting research topic.
But we could make the argument that any model is interpretable in the sense that I can always remove the feature, retrain, and compare the two models, and now I have an explanation of the power of that feature.
How would you compare two models?
Well, compare two models.
You said you remove a feature and then you compare two models. How do you compare?
Well, so I think I want to know the effect of that feature on this model. So I train it with and without the feature. If the performance goes down a lot, then I know this feature is important. So now I can sort all the features. So even though I don't know what's happening inside, I know the effect of all the features, which is a way to interpret the model.
I see. Yeah, this is another idea that I actually thought about when you're working with like deep learning or neural nets. Yeah, remove a neuron and see what that does in order to assign a meaning to it. I think that's a good way to go about, but it's not, in my opinion, and this is it's not direct enough. If you have thousands of neurons in your layer, you're gonna have to train 1,000 models, and training one model takes 4 weeks, and you got to do it over the
derivative of every feature of the objective function with respect to every feature, and now in one iteration over the whole set, I get the answer of the derivative.
If you have idea about
the
this,
features are correlated. We tried that with our splicing work. We trained a neural network. We can predict how a certain gene is going to be spliced. But now for biologists, we want to interpret it and say, well, this is what does that, and this is what does that, and so on. But it turns out features are so correlated that we couldn't get anything interpretable this way. You almost have to you should take derivatives, but with something more complex, and then you have to kind of interpret that too. So it's not as easy.
But basically, when we say things are not interpretable, I kind of object a little bit to this because there's a way to interpret what's happening, but we have to.
Right.
There are things you can do. You can move things from train to test. That tells you a lot. You can train with or without the feature. That also tells you a lot. And you can always remove a feature and then
No, I agree.
and then
You
retrain
should-
without the first
Yeah, yeah.
feature, resort, and now that
And then,
will also
yeah,
take the
yeah,
correlation.
if you're going to
out.
spend a lot of time, everything is interpretable if you're going to spend a time. So maybe the
But
better
I mean,
stance
you
would
can-
be better
it's
wording
automatic.
would be easily interpretable or something.
It's automatic. I can
Yeah.
actually.
Yeah, but once you hold out a feature,
Yeah.
what you get is you now have to hold another feature, and then you have to go back after you group the features and say now, how about this group of features versus that group? It's an iterative process, and it becomes we failed. We couldn't. In the end, we just didn't do it. We didn't do the interpretation of the new one.
This has been my experience too in high dimensional spaces, is that this sort of feature sensitivity analysis starts to break down because of all the correlations between the features. One thing you could do though, which is close to what you're already doing, is you can still do a case-based kind of analysis of what a deep neural net has learned. You go somewhere into the internal representation, do Euclidean distance on the internal representation, not on the original features. And then you can still find cases that are similar to each other, similar to a test example. And if you believe that the cases are intelligible to humans, then you can explain the reasoning of the model by presenting these cases to humans.
Yeah, that's true. I think this comparing feature idea is for the exact reasons that you mentioned. For those who are listening in and can't hear you guys, is exactly right. That it quickly explode in order to enumerate all these questions, and because of this correlation, you can't really tease them out the exact meanings.
But
that
it's
are
not a
included.
bad place to start.
It's not a
just
bad
that
place to
It's actually
start.
a complex research issue.
That's
It's not,
true.
it's not easy.
And also there's what happens if the teacher provides the feature, then you're not going to have that many features, and now you can really interpret what's happening. If the teacher provides the
Right,
feature,
yes.
I mean, if
That's true.
you start from bag of words and you
Humans
let
will-
feature selection do everything because you have a lot of labels, well, okay, you can interpret because you have a huge space. But if you have a small problems which has, you're not only going to label 500 examples because you don't have infinite amount of time, then you probably will provide the feature as well. And if you provide the feature, now you can start interpreting. It doesn't matter what the model is. Now you can actually test it. And of course, you're not going to add correlated features because once you've added the feature, it fixes a bunch of problems. And until the problem that is not explained by the features you put, you're not going to add random features. So
Yes, that's why I was thinking that example you had with circles or any other example, if you actually have an empty table, let people add features, what do they do? Do they actually end up with uncorrelated features or not?
That's interesting. Yeah.
Or
For the
without
coding
feedback, they
example,
end up with
I think they
correlated.
definitely come up with different examples,
The funny
different
thing is that they
features.
think they keep helping, but
Yeah.
but the thing
But
is
with
that the model got it a long time ago with this.
Yeah, for the coding experiment that I did, when I asked them to write down the discovery list, that's kind of identifying the features of the human, all over the place, very different. Once you
put everything in the loop, like what Patrice was saying.
oh, everyone, yeah.
Because if they're all working on that shape problem, and then as somebody adds a feature, it populates everybody's list, and they see that feature, say, oh, okay, I can just click here instead of adding my
Like
own.
the Krauts were saying, where
And then you start automatically erasing some rows which nobody's using, and so on. What happens?
Yeah, that's interesting. That's a more like collaborative way to
Yeah.
build it. Yeah, that would be a next step once we, or maybe together. Yeah. Okay, so the last thing I was going to say is that AI2 is just down the road in U District. If you're interested in and care for machine learning that would benefit humans, I'd love to chat. Thank you.
So feel free to go, but if you've got another question or two, we've got another 5-10 minutes.
Yeah.
I do have a question.
Yeah.
Which is something you sort of skipped in iBCM. You described the way to inject human interaction as a procedure in your Gibbs sampling method, right? So what is the mathematical view of that? Like, so changing Gibbs sampling algorithm is a procedural thing. We have an algorithm to do that. Is there an equivalent mathematical view to say the humans are essentially either changing the prior or changing the likelihood? What is that?
It's kind of providing a new data point, but it's more important data point than original data point, for example. That's a I don't know if it's mathematical, but it's the intuition that I'm going for. That if you have a data point and data points is yelling at some pattern, if you're human that you don't see the pattern that you're looking to see, then it's kind of like creating another data point. And actually this view has been studied. I think it's a paper from MSR that viewing humans interruption as a set of new data points, or like a curriculum of like a principled example. And that's sort of the view that I'm applying here.
Okay.
All right, thank you.
Cool. Thank you, guys. Thanks.